All right, so here is the here's a little help video on circles. I know I haven't been here this week, so here is some some essentials that you'll want to keep in mind for the circle test tomorrow. So if I was a guy taking a multiple choice test with two problems, hint, 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 these would be the things that you really need to keep straight. Okay. I'm getting some help here today because I'm here with my kiddos. So if I have to pause unexpectedly or something like there's a little break in the action, that's because I had to pause and go parent. But everybody's here helping. So Elias, say hi.
Hi.
Marley, say hi.
Hi.
All right. And then I don't know if Ricky will say hi, but she's over there, and we'll see if you start hearing some crying, and well, hopefully it's just her and not me or her mother. All right. Anyways, so here are the things that you absolutely need to know. You need to be disciplined on while you're taking the test. Okay. So while you're doing these things, keep in mind that these things are always true. All right. So when you see questions about these things, stay disciplined to pick these things because the wrong answers are going to be tempting. You know this is true. All right. So this is sometimes more of am I disciplined issue rather than do I actually know the material issue. There's Ricky. We'll see how she's doing. I might pause here in a second, but we'll see. All right. So if here's our circle, all right, and we're moving around the circle. Let's say we're moving around the circle in a clockwise manner. All right. That object on that circle, no matter where that object is, okay, so there's our object going all the way around there. That object is accelerating, even if it's going the same speed. Now, this one is tough because it for whatever reason, we'll word it differently or we'll, just something. People always want to say that the object is not accelerating. It's accelerating. It has to be accelerating if it's moving in a circle. The reason for it is because it is changing direction. Okay? Remember, an acceleration is any change in velocity. Velocity is speed and direction. That means if I change direction, that means I accelerate. So make sure you get that stuck in your brain. I know for the rest of the semester, we've pretty much primarily been talking about speeding up and slowing down. But a change in direction is an acceleration. Okay? All right. Number 2 goes right along with that. Because there's an acceleration, or because the objects are always acceleration, there must be a net force. Okay, so there is always a net force. Okay, that net force is the centripetal force. All right, so how we've treated net force in the past is how we want to treat centripetal force. It is the centripetal force. Okay, so we'll talk about that more as we go. All right, next, inertia plays a huge role here. Because inertia causes this object to try to move in a straight line. It is trying to move in a straight line. This is what's happening, okay? But every time it tries to move a straight line, there is a force that causes, and that's that net force, that's that centripetal force that pushes that object towards the center of the circle, all right? And so the object is trying to move in a straight line. Some outside force pushes it towards the circle. Okay? You will notice there is no circle, there is no force from the middle of the circle pushing out to keep it at that point. Okay? That's called a centrifugal force, and it is a fictitious force. Okay? Now, you may recall in vertical circles, there are times where forces point away from the center of the circle. That's not a centrifugal force. because at the other end of the circle, that same force points towards the center of the circle. So that's just a matter of direction, has nothing really to do with it being a centrifugal force. Okay, so don't get those confused. All right, number 4. All right, as I erase here, number 4 is centrifugal forces are fictitious forces. There is no such thing as a centrifugal force. Remember the line I used. These things we call, go ahead, bud. These things we call centrifuges really shouldn't be called centrifuges. They should be called inertiafuges. All right? That pretend force that actually pushes things out or whatever is not a centrifugal. It's not a force. It's inertia. Inertia is not a force. So don't fall for that either. Okay? So there is no such thing as that. So that is very important that we understand. Right? And sorry. The reason we come up with that force, the reason that people say there has to be a force, is because they're trying to observe what we call non-Newtonian motion, right? So they're seeing some motion they can't explain, and they they invent a force to try to explain it. Remember the CO2 puck on the turntable. It looked like it was traveling in a circle, but in reality it was traveling in a straight line. The reason you thought it was traveling in a circle is because you were in a bad reference frame, because the camera was spinning in a circle. Okay? All right. Number 5. The acceleration of an object moving in a circle is always towards the center of a circle. This is huge, right? So if I draw the object, let's say I'm going to draw the object at the top of the circle and it's going around clockwise like that. It's trying to move in a straight line. So this is its instantaneous velocity at that moment. At that moment, to get that velocity to change direction, we must accelerate this way. It's 90 degrees. It's a 90-degree angle. That's the acceleration. So if I'm here, the straight line velocity is that way, the acceleration is that way. If I'm here, the straight line velocity is that way, the acceleration is that way. If I'm here, straight line velocity, there's the acceleration. If I'm here, straight line velocity, there's the acceleration. The acceleration is always 90 degrees. Always 90 degrees. Because it's always 90 degrees, it's always pointing at the center of the circle. So the acceleration always points in the same direction. It points at the center of the circle. Okay? Now, because the acceleration always points towards the center of the circle, that means that if we're looking at number 6, that means the net force is always pointing towards the center of the circle. Okay? Now, the net force, is the centripetal force. Okay? So if we're, so this is like number 6 and number 7 combined. If you remember when we were drawing like a vertical circle, okay, and we're going to do like a Ferris wheel. All right. Remember, we draw these at the top of the circle and at the bottom. So at the top, what we get is we get a force of gravity down and we get a normal force up. Because at the top of the circle, the centripetal acceleration, as we just discussed, is down. So like if we're in the circle, this is where we're at right there. That's the top. All right. That means if we're going around this way, the acceleration is towards the center. It's down, okay? In this case, FC, all right, would be equal to, this would be FG, would be equal to FG plus F norm, okay? And in this case, F norm would be negative and FG would be positive. Why? F norm's pointing away from the circle, so it's negative. And FG is pointing towards the circle, so it's positive. Okay, at the bottom of the circle, so down here, right? Let's go over here to do this. So we'll be over here. We draw our free body diagram. F norm is now up, and the force of gravity is down. Release, right? The acceleration up here would have to be up towards the center of the circle. So here's your acceleration right there. Our centripetal force is still the net force, which is F norm plus Fg, right? In this case, F norm would be positive because it's pointing towards the center, and Fg is negative. This is why they're not centripetal forces, because there's no one force. There's not one force that always points away from the center of the circle. Now, keep in mind that Fc, because it's a net force, is still equal to mass times the centripetal force. And this can take a variety of looks, right? Usually the most common variety is just v squared over r. That's the easiest way to look at centripetal acceleration. But you can also look at it, it's the 4 pi squared r over t squared, or 4 pi squared r over not over, but times frequency squared. Okay. All right. Yep. Now let's talk about number 8. So vertical circles. Now a vertical circle is one of two categories. It's either a Ferris wheel or it's a ball on a string. And hold on. We're going to try to speed this up a little bit. Woo.
Uh-oh.
All my stuff disappeared. Oh, man. All my stuff disappeared. All right. So anyways, I'm going to just keep going. Number 8 was all circles are ball on a string or vertical circles. So if we're doing a Ferris wheel, okay, the way you tell the difference is at the top of the circle. There's always two forces. So there's a force of gravity, and at the top of a Ferris wheel, there'll be a normal force. Okay. If you're doing a ball on a string, at the top of the circle, there will be a force of gravity down, and there will be like a tension or some other force pushing the object down. So the difference is the two forces. If one force is down, one force is up, then it's a Ferris wheel. If it's both forces down, then it's a ball on a string. All right. Next was both of them can have a weightless velocity. So for a Ferris wheel, there is a certain velocity, all right, where an object feels weightless, okay? That weightless is when you can't feel the net force. So the only force acting on it is the force of gravity, which means that the centripetal force is equal to only gravity, which would mean, all right, which would mean, as you guys all know, the centripetal acceleration should just equal gravity, okay? With a ball on a string, it's the same concept. It is the exact same concept, okay? The force of gravity is here. We would not feel any other forces, so that tension that's down, we wouldn't feel that. So again, the centripetal force would equal the force of gravity, and the centripetal acceleration would just be equal to gravity. So that's another way of me saying it. If I say, in which situation is the centripetal acceleration equal to gravity, that's referring to the weightless velocity, okay? Now, the weightless velocity does not depend on mass. It only depends on how fast you're going. And so if you hit that weightless velocity, then you're going to feel weightless. Now, if you take a look at these two, okay, for one of them, that weightless velocity is a maximum, and for the other one, it is a minimum. All right? Over here on the Ferris wheel, this is a max, right? If you go any faster, that normal force is already gone. You're going fast enough that normal force is gone. That means your rear end is already just floating off of your chair there. Shh, thanks, sweetheart. And so if you go any faster, what ends up happening is there is no more downward force. We can't recruit more gravity for you. All right, so there's less force down. What ends up happening is you go faster, you